Hi, this is the Youngstown State University PIC Math Group preparing for industrial careers in mathematics. We've been advised by Dr. Tom Wakefield from YSU, and our project is redistricting police beats in the city of Youngstown, Ohio. So now I'd like to introduce Christy Asback.
So first we're just going to discuss a brief outline of what we did in this project. We'll start with some background of the problem as to why we did the project, move into our problem statement and goals, and then further on to methodology, results, and our implications. So just a little bit of background on the problem. Police officers patrol geographical areas in the city known as beats. However, the beats in Youngstown, Ohio have been unchanged for over a decade. And I'm sure you can imagine that over that length of time, the crime has migrated and changed, so the workload across the beats is now very unequal. The Youngstown Police Department did conduct some analysis, however, it turned out to be inconclusive, which is why we are tackling this problem. So first we looked at some historical workload that was given to us by the police officers from November of 2013 to November of 2014. And we can see based on these descriptive statistics that the total number of calls is very unequal. First, throughout the beats, you can see that, such as in beat 109 and 209, there is a very high amount of calls, whereas in 106 and 108, a very low amount of calls. Next, if we move over to the upper right graph, we see the total calls by priority. Now, each call when it comes in is given a priority, either a 0, 1, 2, or 9, 0 being the most dire situation, 9 being the least. We can also see on our bottom graphs that it varies through the days of the week and through hourly. You can see there's a big dip in the AM and it gradually increases throughout the afternoon hours. So once we looked at all this data, we came up with our problem statement and we decided to divide it into 3 stages. First, we want to redistrict our beats, then we want to assess the changes and compare them to the old beats, and finally we wanted to schedule our police officers. But we also needed to keep in mind that we wanted to create contiguous and compact beats so our officers did not have to travel a long distance when responding to a call. And we also needed to consider the local geography because crossing over a river or a park would create an excess amount of time. We also wanted to create a metric to measure our local workload so that we can really quantify a number for each cell in our beats. So now we're going to look just a little bit at that metric. It really played an integral part in our project because we needed to quantify weights in order to move on with our geographical boundaries. So first we let our geographical area of Youngstown be a matrix of 42,000 cells, which we'll get into a little bit later. And then we weighted each of these cells according to this equation. 0.5 times the total number of calls in one cell over the max total of calls in all the cells, plus 0.5 times the priority sum in one cell over the max priority sum in all of the cells. We were able to quantify the priority sum by discussing with the police officers, and they told us which situations needed what kind of weight. And we also chose 0.5 as our beta estimates because when discussing with the police officers, they said that the total number of calls in the priority had about an equal importance when responding to a call. So next, I'm going to hand it back over to Eric, who will discuss the geographical aspect of our project.
So as we begin to tackle the problem of creating new beats in the city of Youngstown, we wanted to familiarize ourselves a little bit with the local geography. So here's a map of Youngstown, and you can see what are U.S. Census blocks. Census blocks are the smallest geographical unit that the U.S. Census Bureau aggregates data for, including information like how many people live in each of these little areas. And these are important because they follow local roads and rivers and local boundaries that the police felt were important when we went to create our beats. So in addition to our local boundaries, such as a road, the police department felt it was very important that our beats be mindful of geographies including rivers and parks that are difficult to cross easily. So you can see here in blue, our map has our boundaries that we're not going to allow our new beats to cross. As Christy mentioned, we overlaid a grid of 42,000 cells over the city of Youngstown. And here's a representation of what that looked like. So each cell, we then calculated a workload weight for, as Christy mentioned. And here's what that looked like when displaying the data in MATLAB. And you can see that you can start to notice a spatial distribution. Areas with red cells have higher workload scores, and areas with light blue or dark blue have either no workload or very low workload scores present. So now I'm going to hand it over to Jenna Wise as she's going to discuss our growth algorithm.
uses the weight matrix we talked about previously, and then it also uses geographical matrix. So the geographical matrix actually contains 0, -1, or 1 through 13, or 14 depending on the number of seeds or beads in each cell. And a -1 means your geographical boundary, and a 0 means that a cell can be taken by a bead. And of course 1 through 13 means that you're part of that number of beads. Now our algorithm actually follows the following steps. Each cell, or each bead or seed grows one step at a time in an incremental fashion. And in each step, it follows one of 3 steps. So it'll identify the cells that it can take, or the possibilities that it can take, and those are just the cells adjacent to the beat, the current beat. And then it'll select from those possibilities from highest to lowest, depending on the weight matrix we talked about previously. And it will select from the highest to lowest until it reaches one or two of 2 capacities, either the global capacity or the local capacity. And then finally, it'll update the geographical matrix depending on the selected possibilities. Now, all beads will grow in this fashion until they reach capacity, and we grow incrementally so that we break ties between cells that each bead wants. Like if both beads want to take the same cell, we break those ties that way. Now, selecting our initial seeds or our initial placement for our beads is a very important task for our algorithm. So we generated in MATLAB a visual of our weight matrix so we can see clusters of crime, based also with the overlay of our boundary. So we triangulated points or our seeds around those clusters while equalizing the space between them. So after we do this on a trial basis, because we select our seeds and then when we grow them, sometimes they don't always work. As you can see here, we have open space where beads haven't reached, so they are compact or contiguous. And so we actually did 5 trials until we got our first alternative, and there's not that much difference between the initial seeds we had previously and the initial seeds we have for alternative 5, but now we have contiguous compact beads. Now let's get into, we actually generated 5 alternatives, but we'll look at 2 here. This is alternative 1, generated in MATLAB. It has 14 beads, and it's compact and contiguous. And now we overlaid that using ArcGIS using census blocks. So now the YPD can use them in the future. And so we also want to look at alternative 3. This one actually only has 13 beads, and the beads are slight variation between the previous one. And again, here's the overlay for census blocks. Now I'm going to pass it off to Ashley Orr to assess these new beads.
So as Christy mentioned at the beginning of our presentation here, that a problem for our project was the unequal workload that the beats had. So once we created that metric where we were weighting the volume of calls along with the priority of each of those calls, we were able to look at the original metric per beat and then compare that to our results, or each of our 5 alternatives. So using that historical data, the figure here on your left is the original metric per beat. And you note that there's a high variation among the different beats, and this is something that we want to correct with our alternative or our results. In the figure on the right here is the alternative 1's metric for each of the beats that were proposed in this alternative. And we went ahead and did this for each of the 5 alternatives that were proposed, and they're seen here. Jenna mentioned alternative 3, which she showed matched to the census blocks. And we note that this is one of our best outcomes for our results, as that if you look at the histogram that has the graph of the crime workload metric, it's equal or relatively equal across each of the beats. We note that in each alternative, beat number 4 has the largest crime and priority value, thus making it 1. But to further assess or kind of quantify that equalization, we calculate the summary statistics or the descriptive statistics across the crime metrics. And because we're not necessarily looking at a measure of center, but a measure of spread, the variation of calls and the priorities across the beats, we want to look at the standard deviation and the coefficient of variation to see if our results are working. Here we see the alternative and then each of the or the original on each of the alternatives, and we note that for each alternative, the standard deviation is actually lower than the original, and that the coefficient of variation, which works to compare the mean to our standard deviation, is reduced by as much as 37%. So we can conclude that our problem of high variance has been reduced. So moving forward, I'll pass this off to Sebastian, who will address the scheduling of the police officers.
So our final stage of the project was to have a scheduling recommendation as far as whether we should have, by what hours of the day, whether we should have one officer versus two officers. And so we were able, as Christy mentioned, we were able to get a look in a similar method of our metric by day of the week and by hour of the day. And we got an average metric in each beat by hour of the day, and they have a similar trend. This is layout alternative 3, and by hour of the day they have a similar trend across all the beats. And we notice a dip, below 0.4 in our metric between the hours of 1 and 9 o'clock in the morning. And so we just recommended that during those hours we have 1, and then for the rest of the day that we have 2 officers in each beat. We also wanted to look at different things for further research, and so we could identify a more precise method for initial seed placement. We want a little bit less sensitivity in our algorithm to initial seed placement, and factor in other considerations, including the population of census blocks. So I'd like to pass this off to Mr. Shahadi.
Thank you. We'd like to acknowledge a few groups, including the YSU Math Department, Department of Geography, the YSU Police Department, the Youngstown Police Department, and the Mathematical Association of America, and our advisor, Dr. Tom White.